Very happy today. Yeah, thanks, please. Thanks for the audience to come and for coming, and I'm very happy today to be hosting Gustavo's talk. So Gustavo is not only a collaborator but also a friend in the last years, and it's always very interesting to hear he talking about physics, and I hope you all enjoy the seminar with him. So Gustavo was in the beginning of the year in the University of Southern Denmark, and now he's a professor in the São Paulo State University. And today you will hear him talking about if quantum gravity can trigger chiral symmetry breaking. Okay, so thanks Gustavo for agreeing to give us this talk.
Okay, so thank you, Gabriel, for the warming introduction. And I would like to thank the organizers for the invitation. This is actually the second time that I'm giving a seminar in this seminar series. I think I was just checking here, and my first seminar was one of the first seminars in this seminar series, almost exactly 2 years ago. So it's nice that, I mean, has been already more than 2 years that this initiative is going on. So yeah, and congratulations for keeping this alive. So as Gabriel already mentioned, I will talk about the interplay between chiral symmetry and chiral symmetry breaking and quantum gravity. And this is more or less the outline of my talk. I will first give an introduction on why to look at chiral symmetry breaking, what is the possible connection with quantum gravity, and how do we actually can investigate this. And then I will start to talk about chiral symmetry breaking, and I mean the possible interplay between chiral symmetry breaking and gravity in two different non-perturbative frameworks for quantum gravity. The first one is quadratic gravity, especially based in a kind of analogy with QCD. And the idea is to investigate whether light fermions are compatible with this scenario for quantum gravity. And the second one is, the second approach is the asymptotically safe quantum gravity. And the idea here is to investigate whether light fermions with charge and also with color, they are also compatible with the asymptotically safe landscape. So let me first start with the question, what can we learn about gravity from chiral symmetry breaking? So the idea is that chiral symmetry breaking is deeply connected with fermion masses. And a very easy way to see this is consider, for example, a Dirac fermion. We can decompose the Dirac fermion in terms of its right-handed and left-handed components, so in terms of Weyl fermions. And for example, if you look at standard terms that can show up in a Lagrangian for a Dirac fermion, we have the kinetic term, which we can also decompose in terms of something that just involves the right-handed components and something that just involves the left-handed component. And if we look at a typical mass term, then this kind of decomposition involves something that mixes. I mean, we cannot decompose in terms of right-handed and left-handed only components. So we always have a mixing between the right-handed and left-handed chiralities. This basically means that the kinetic term is invariant under chiral symmetry. So you can perform a rotation, a chiral rotation, in which one of these terms and they individually are preserved, the form are preserved individually. But the typical mass term, the typical Dirac mass term, this is not chiral symmetric precisely because you have this kind of mixing, then you cannot independently perform a rotation in the chiral components. Okay, so this basically means that the existence of massive fermions indicates some form of chiral symmetry breaking in nature. There are multiple ways in which you can do that. So for example, you can have an explicit chiral symmetry breaking term in the Lagrangian. So you just add by hand some chiral symmetry breaking term, or you can also have some kind of mechanism associated to chiral symmetry breaking. This mechanism can be some form of a spontaneous or a dynamical mechanism. And this second version is the way is the version that I'm going to explore in my talk. So before looking into gravitational physics, let me give some example about chiral symmetry breaking in non-gravitational physics. So for example, we can think about the relation between chiral symmetry breaking and what we call magnetic catalysis. So the idea here is you have a fermion, you couple this fermion to an external magnetic field. This kind of coupling, so if you look, for example, at a three-dimensional system, this kind of coupling between fermion and an external magnetic field generates some form of effective dimensional reduction of the system. And this dimensional reduction happens because of a change in the spectrum of the Dirac operator in the Lagrangian. And as a consequence of this kind of dimensional or effective dimensional reduction, the system essentially develops a chiral symmetry breaking. And that's what we call a magnetic catalysis. The second example, the second non-gravitational example, and this is more closely related to what I'm going to discuss in my talk, is the example of chiral symmetry breaking in the context of QCD, in the context of quantum electrodynamics. Quantum chromodynamics. So in QCD, you know that, for example, hadrons, they are composed by, they are formed by bound states of quarks with interaction mediated by gluons. And one property of this kind of bound states is that if you take, for example, a bound state that corresponds to a proton, and if you look at the mass of the proton is much larger than the mass of the individual quarks inside the proton. The masses of the quarks, they essentially comes from the electroweak spontaneous symmetry breaking. So the lesson that we learn from here is that the mass difference should come from something else. And in the context of QCD, the something else is essentially this mass difference comes from non-perturbative effects related to gluon fluctuations. So the fluctuations that are responsible to form the bound states, they also contribute to the mass of the bound state. Okay, and this is another example of chiral symmetry breaking or a dynamical chiral symmetry breaking happening in a physical system. In this case here, more related to fundamental interactions. Okay, so far, no gravitational physics. Let's then start to add gravity and try to understand what we can, how we can relate gravity to chiral symmetry breaking. The first way we can relate gravity to chiral symmetry breaking is based on an analogy with magnetic catalysis. So the idea here is that gravity also changes the space-time geometry. So you have let's say, you have a background gravitational field. This background gravitational fields produce modification in the background geometry or produce some effect on the background geometry of space-time, which means that gravity affects the way that fermions propagate. In a more technical sense, this means that the background structure related to gravity changes the spectrum of the Dirac operator. And in the same way that this happens in a background magnetic field in the mechanism of gravitation of magnetic catalysis, in this case here, we also have some form of effective dimensional reduction related to curved background. And so this generates some similarities with magnetic catalysis. And this is what we call a gravitational catalysis. So it's possible that a background curvature changes the Dirac spectrum, the spectrum of the Dirac operator in such a way that we have some form of catalysis that produces a chiral symmetry breaking related to a background geometry. So a background space-time effect. This has been investigated in the context of curvature induced gravitational catalysis a few years ago by Holger Gies and Ricardo Martini. And what they found that in their investigation is that indeed you can relate background curvature with a generation of fermion masses. More recently, with Arthur and Antonio, I think Arthur is also here in the audience, we looked at a similar question, but in the context of background geometry with torsion. So instead of a curvature-induced gravitational catalysis, we were trying to search for torsion-induced gravitational catalysis. And what we found in this case was that, differently from torsion, if you have gravity encoded in the form of background torsion, we don't have a mechanism of gravitational catalysis. Okay, so this is not the focus of this seminar. So this is just an example of how gravity can be related with chiral symmetry breaking. The focus of this seminar is to relate quantum gravity fluctuations with chiral symmetry breaking, and in particular whether quantum gravity fluctuations they can trigger chiral symmetry breaking. So the first point here is, why should we expect this? Naively, we can expect that quantum gravity fluctuations can trigger chiral symmetry breaking because gravity is an attractive interaction. So this means that this favors the formation of condensates, or naively it favors the formation of condensates in the same way that happens in QCD. And if this happens in a non-perturbative regime, for example, around the Planck scale, then we would expect a generation of fermion masses of order of Planck scale. For example, this is what we could expect in the context of asymptotically safe quantum gravity, where we expect that gravity becomes non-perturbative around the Planck scale. So if this happens, then if gravity indeed triggers chiral symmetry breaking around the Planck scale, the first consequence is that this would generate fermion masses around the Planck mass. And this is, of course, a clear violation of what we observe, or a clear incompatibility with what we observe in our universe. So in our universe, we observe light fermions, so fermions with masses much lower than the Planck mass, and therefore avoiding chiral symmetry breaking in gravitational systems or associated with quantum gravity fluctuations may impose non-trivial constraints in a quantum gravity theory. So that's the main investigation, or the main topic that I want to address in this talk. If you want to take a nap during the rest of my talk, this is basically the take-home message. So essentially, the idea is that we need to avoid chiral symmetry breaking induced by quantum gravity around the Planck scale. And this is a requirement related to phenomenological viability. We want to describe light fermions because we observe light fermions in the universe. Doing this, investigating whether a chiral symmetry breaking is related to or can happen in non-perturbative approaches for quantum gravity lead to the conclusion that both in asymptotically safe quantum gravity and also in a setup of quadratic gravity based on QCD, in analogies with QCD, we find that we can avoid chiral symmetry breaking in both setups, and I will discuss this in more detail in my talk. But in principle, we can also impose some constraints on the matter sector from this interplay between chiral symmetry breaking and quantum gravity fluctuations. Okay, so this is the take-home message, but now let me tell you how to get to this message in my talk. So the first point that I want to discuss here is how to identify chiral symmetry breaking. So the idea is that I will try to identify chiral symmetry breaking by looking at the flow of four fermion interactions. So interactions of the form of Nambu-Yonah-Lazino model. So I have here a standard Dirac a kinetic Dirac term, a kinetic term for Dirac fermions, plus 4 fermion interactions involving a vector channel and also an axial vector channel. The idea here is to look at the renormalization group flow of this 4 fermion coupling. And for example, using the functional renormalization group to explore this the flow of 4 fermion couplings, we get this kind of structure for the beta functions and this kind of structure for the flow, where this hash here basically denotes some number. And the idea is that we can relate divergences on the flow with the formation of condensates. This basically means that we can separate trajectories or RG trajectories in regions where we have chiral symmetry breaking and regions where we don't have chiral symmetry breaking. So for example, in this simple example here, in this simple RG trajectory described by this expression here, we have a critical value such that below this critical value, the coupling decreases towards the infrareds, therefore avoiding chiral symmetry breaking. And above this critical value, the coupling tends to a divergence in the infrared, therefore approaching chiral symmetry breaking in the infrareds dynamically. Okay? In a more realistic setting, we want to investigate this, including a fierce complete basis, so all possible 4 fermion interactions compatible with the symmetries. So for example, if we just have flavor, a bunch of fermions with characterized by different flavor number or flavor index, essentially we have two independent channels of 4 fermion interactions. And in this case here, the idea is that we can identify signs of or indications for chiral symmetry breaking by looking at the phase diagram of the different, involving the different 4 fermion couplings. And the idea here is that, so for example, this is so far without gravity. Without gravity and using the FRG, the functional renormalization group to compute the flow of 4 fermion interactions, we can basically arrive at a phase diagram of this form here. And this green region here essentially is the region where the couplings flow to the infrareds towards this fixed point, this Gaussian fixed point in the infrared. So the idea is that any UV ultraviolet initial value within this region, this green region, is safe from chiral symmetry breaking. So we can always define a chiral region such that we avoid chiral symmetry breaking in this kind of system. Okay, so now we start to add quantum gravity effects. And the idea here is that now I'm going to add fermions to dynamical gravitons. And I'm going to do that using some form of background formalism. So I decompose my full space-time metric in terms of a background metric plus fluctuations. This starts to generate vertices between gravitons, so the fluctuation fields, and fermions. And now if you look at the structure of beta functions of 4 fermion couplings, then we have new contributions involving the gravitational coupling. So in this case here, I'm just using the Newton coupling as the gravitational coupling. Okay? In particular, this kind of contribution here highlighted is important because this is a kind of induced contribution. This does not involve the 4 fermion coupling itself. So the idea is that once you so without gravity, if you look at the beta function for a 4 fermion coupling, so this is the case where gravitational coupling is equal to 0. If you look at the beta function, we have these two fixed points, and the region between the fixed points define the chiral symmetric phase. And once we start to add gravity, it's possible that we shift this beta function upwards or downwards And here I'm concentrating on the possibility of shifting it upwards. If this happens in such a way that for a value of the gravitational coupling above a critical value such that we don't have any any fixed point anymore, then we can no longer define a chiral region or a chirosymmetric region. And therefore, I mean, if we get to this kind of situation in quantum gravity, then we cannot avoid gravity triggering chirosymmetry breaking. So the idea here is that if this kind of situation happens in quantum gravity, then chirosymmetry breaking would happen if the gravitational coupling exceeds a certain critical value. So that's just what we can expect from renormalization group flow involving four Fermi interactions plus gravity. Okay, but the idea is to see that if this is indeed what happens once we go to a quantum gravity, to a specific quantum gravity approach. So in order to explore whether this indeed happen or not in systems involving gravity plus fermions, I will employ the function renormalization group 2 or the function renormalization group method. And the idea here is essentially we perform a kind of Wilsonian integration of a pathing integral. So instead of performing a full integration of the pathing integral at once, basically we perform an integration in terms of momentum shells or mass shells. And the way that this is done in the functional renormalization group is by introducing this flowing effective action, gamma k, which essentially encodes the effective dynamics above a certain infrared scale k. So this infrared scale is determined by an infrared cutoff. And the way that this is implemented in the calculation is by adding this kind of infrared regulator that acts as a kind of momentum-dependent master. Okay? The nice feature about this kind of formalism is that this functional gamma k, this flowing effective action, this is associated to an exact flow equation. So we can write, at least formally, an exact non-perturbative flow equation, renormalization group equation for this functional gamma k. Once you solve this, I mean, if you can solve this flow equation, then you can solve the quantum dynamics of the theory. Of course, that in practice, we cannot solve this exactly, which means that we need to employ truncations. And this is basically done by expanding this function in terms of operators that are compatible with the symmetries of the theory. And this is, I mean, this is basically what defines the theory space of a given model. And one important disclaimer about the results that I'm going to present here is that since I'm using this functional RG as the tool to explore chirosymmetry breaking, all the calculations that are done in the Euclidean setup, and it's not clear if there is a clean correspondence between these Euclidean results and Lorentzian results. And another important point is that, as I mentioned before, we need to do some kind of approximation in order to extract some information from this flow equation. And this approximation is in terms of FRG truncations. So essentially, we consider a finite number of operators as an ansatz for my gamma k. And then I basically run the RG machinery in the subspace defined by a finite number of operators. The problem of employing FRG truncations is that we don't have a systematic way of controlling the systematic errors. So a lot of things that I'm going to talk here, they are more exploratory, and it's not clear whether they are really under control from the point of view of theoretical errors. Okay, so let's keep this disclaimer in mind. Okay, so let now I start to talk about results and talk about more I mean, the new investigations that I did in the past years and that I'm going to talk about today. So the first one is exploring quadratic gravity in analogy with quantum chromodynamics. And the answer that I want question that I want to answer at the end of this part of the seminar is whether chiral fermions or light fermions, if they are compatible with the landscape of this kind of quantum gravity setup. So let me just take a sip of water. Okay, so before talking about chiral symmetry breaking, let me first talk about the setup that I want to investigate. So the idea here is to investigate chiral symmetry, is to investigate quadratic quantum gravity. And the idea is that quadratic gravity, and by quadratic gravity, I mean Einstein-Hilbert plus curvature square terms. This is in principle a possible UV complete scenario for quantum gravity. And the way we can see this is that if you look at the three-level propagator in quadratic gravity, then you have the propagator essentially behaves with 1 over q, 1 over momentum to the power 4, instead of 1 over momentum square as it happens in GR. In the context of perturbation theory, this basically means that quadratic gravity is perturbatively renormalizable as a quantum theory. And more than that, quadratic gravity is also, at least there is a region in the phase diagram of quadratic gravity of these couplings F2 and F0, where you can define asymptotically free trajectories in the theory. So this basically means that, in principle, this would mean that we have a theory that is both perturbatively renormalizable, but also UV complete. So why, I mean, based on this, why don't we claim that we have already a theory of quantum gravity? And the reason is that, at least the traditional point of view regarding quadratic gravity is that we have issues related with unitarity. And these issues are basically connected to this minus sign here in the propagator, which correspond to, which basically give rise to negative norm states. So states that correspond to ghost-like states in the theory. More recently, there was a couple of proposals on how to solve the ghost issue or the unitarity issue in quadratic gravity. And the version that I'm interested to explore here is based on analogies between quadratic gravity and quantum chromodynamics. And the idea is the following. So if you look at quantum chromodynamics, essentially we have a situation where we have an asymptotically free theory in the ultraviolets, a microscopic asymptotically free theory, essentially Yang-Mills theory. This theory becomes strongly coupled in the infrared. Something happens here which basically changes the asymptotic states of the theory. So the idea is that in the ultraviolet or above this QCD scale, what would correspond to asymptotic states are the gluons and quarks. And we know that they are actually confined in the infrared. So they actually generate bound states, and they are more than that, they are confined. So which means that they cannot appear as asymptotic states in the tube. Okay, so the proposal is that the same thing could happen in quadratic gravity. So in quadratic gravity, we also have asymptotic freedom in the ultraviolets. Here in the ultraviolets, we expect that the theory has a massless healthy state, but also a massive ghost state. And this ghost state is the problem with quadratic gravity. And then the conjecture here is that we enter in a non-perturbative regime. And this non-perturbative regime would essentially remove the ghost-like states from the spectrum of the theory, from the physical spectrum of the theory. So that's essentially the idea behind the conjecture by Bob Hodo and Rain, where so the idea is, as I said before, so if we try to formalize this in terms of propagator, so for example, if you look at the three-level propagator in Yang-Mills theory, essentially what we have here is a 1 over q square propagator, so massless massless free particles essentially as asymptotic states. And if you look at the Dirac propagator, including non-perturbative effects, now you have this kind of Dirac functions that can remove the poles associated to these massless states. So for example, if you look at QCD and if you look at the gluon propagator, so the gauge field propagator computed from the lattice, and if you do a fitting of this propagator, you get this kind of form for this Dirac function. And the fitting with the lattice data essentially suggests that we have some, instead of having real poles in the propagator, we actually have complex poles. And complex poles in principle do not have a particle interpretation, which is an indication for gluon confinement, or at least it's a possible, I mean, it can possibly be interpreted as an indication for gluon confinement. So the idea here is that this conjecture by Hodo and Rain is that the same kind of things can happen in quadratic gravity. So if you look at a three-level propagator, then we have this 1 over q to the 4 decay. Now, if you look at the Dirac propagator, we would have this Dirac function. And the idea behind the conjecture is that non-perturbative effects around the Planck scale, they could remove the ghost, so the massive ghost from the physical spectrum of the theory. So that would be the way to deal with the unitarity problem in quadratic gravity from this perspective based on QCD, so based on analogy with QCD. So far, this is still a conjecture. So no one actually explored this, at least not that I'm aware. No one ever explored this non-perturbative regime of quadratic gravity. But before exploring this non-perturbative regime to see if this scenario is indeed realized, we can ask the question whether this kind of scenario can generate other kind of problems. So for example, in the context of QCD, this non-perturbative regime generates chiral breaking around the QCD scale, which basically means that we have fermions, in this case hadrons, with masses around the QCD scale. This is, of course, a desirable mechanism in the context of QCD, because this is what explains the mass of most of our visible universe. But if the same thing happens in quadratic gravity, this would be an undesirable mechanism, because this would be incompatible with the existence of light fermions in our universe. So incompatible with the existence of fermions with masses much smaller than the Planck mass. So this is a consistent check for this approach. And this is what I did in a work that I published in the last year. So the idea was to set up an FRG calculation. So essentially using an FRG truncation involving quadratic gravity coupled to fermions, including 4 fermion interactions. This leads to flow equations for the 4 fermion interactions, including contributions from quantum gravity. Of course, we also have beta functions for the gravitational couplings. And in order to search for indication of chiral breaking in this kind of setup, I tried to look at 3 different questions. The first was how gravity deforms the fixed point structure of the 4 fermion couplings. The second one is how gravity deforms the phase structure of the 4 fermion couplings. And the last one is how gravity directly impacts the RG trajectories of the four Fermi couplings. So let me try to answer these three questions and then try to convince you that there is no indication for chiral symmetry breaking in this kind of setup. Okay, the first one is how gravity deforms the fixed point structure of these beta functions for lambda plus and lambda minus. So for the beta function for the four Fermi couplings. And this plot here essentially shows the fixed point values for lambda plus and lambda minus as a function of gravitational couplings. I'm setting one of the gravitational couplings to 0 just as a benchmark values, but I actually tested different values and the qualitative discussion is essentially the same. And what we find here is that gravity indeed changed the values of the fixed point. Change the fixed point values for the four Fermi couplings. That's of course expected because the beta functions depends on the gravitational couplings. But we see indications for fixed point collisions. So possible collisions that could, in principle, annihilate the fixed points. But this is not what happens here. We do have fixed point collisions, but all the fixed point values remain real values. So the punchline here is that gravity indeed affects the fixed point structure of four Fermi couplings, but not in such a way that we have a fixed point annihilation. We do have fixed point collisions, but the fixed point remain real valued. Okay, and that's one of the criteria to avoid chiral symmetry breaking. The second question was how gravity deforms the phase structure of four Fermi couplings. And here I'm concentrating in three different regions of the gravitational couplings, just as benchmark examples, but I also explore different values and the qualitative results are unchanged. And here we see that depending on the region on the space of gravitational couplings, we do have different phase diagrams. So there is a difference on possible on the possible phase structures. But in all cases, we still can, in all cases, we always can define a chiral region, this region in green here, such that ultraviolet values are connected to infrared values that are finite. They are connected via RG trajectories to an infrared values that are finite. So in all cases, we do have a chiral region that remains intact. So this is another indication that the different values of the gravitational couplings, in this case here, they do lead to different phase structures, but in all cases, it's still possible to define a chiral phase such that chiral symmetry remains intact in the infrared. By infrared here, I mean anything that is not the deep UV. So, for example, a possible chiral symmetry breaking in the infrared would be already at the Planck scale. Okay, so and that's what we want to avoid. So we want to avoid chiral symmetry breaking around the Planck scale. Okay, so that was the second test. The last question was how gravity impacts the RG trajectories. And for that, I indeed performed the integration of the four Fermi beta functions together with the running of the gravitational couplings. And here I see that the four Fermi couplings remain finite towards the infrared. This left panel here, corresponds to the gravitational, so fermions plus gravity case. The right panel corresponds to gravity plus toy model for QCD case. And we see this clear difference here. In the case of gravitational, in the case of gravity, of quadratic gravity, we independent, I do have these different trajectories correspond to different values of gravitational couplings in the infrared, sorry, in the UV, or around the Planck scale, sorry. And in all cases, we see that the trajectories remain finite towards the infrared. In QCD, for example, if we exceed a certain critical value, then we run towards a Landau pole in the infrared. And this is a qualitative difference between what happens in quantum gravity and what happens in QCD. There is a very important caveat here that in order to actually perform this integration, I'm imposing a kind of toy model trajectory by hand for the gravitational couplings, because I would need to have control of what's going on in the gravitational sector in this non-perturbative regime in order to perform a fully consistent integration. And at the moment, I don't have this. But I can tell you that a similar toy model also generates, I mean, this kind of trajectories here in the case of QCD. This was also done with a similar toy model for the running of the gauge coupling in QCD. So that's, at least in my opinion, an indication that things are at least qualitatively consistent in here. Okay, so going back to the original questions. So the first question was how gravity deforms the fixed point structure of performance couplings. And the punchline here was that, or the answer of this question was that the gravitational fixed point structure is deformed, but all the fixed point values remain real. The second question was how gravity deforms the phase structure of the performance couplings. And the answer was that we do have different phase structures depending on the gravitational couplings around the Planck scale, depending on the value of the gravitational couplings around the Planck scale. But we can always define what we call a chiral phase, so avoiding chiral symmetry breaking. And the last question was how gravity impacts the RG trajectories for the four-Fermi couplings. And what we found was that the integrated trajectories result in four-Fermi couplings that are finite towards the infrared. And this is a significant difference in comparison with QCD. So at the end, we found no indication for chiral symmetry breaking in the context of quadratic gravity, which is good. We want to avoid that, which basically means that, at least from this first investigation, this approach seems to be compatible with the existence of light fermions in nature. Okay, Gabriel, how much time do we still have?
6 minutes.
6 minutes.
Yes.
So if I just have 6 minutes, let me try to really summarize what's going on in the context of asymptotic safety. So first of all, what is asymptotic safety? And I would be very brief with that. Asymptotic safety is another non-perturbative approach for quantum gravity, which is based on the renormalization group language. It's based on quantum scale symmetry. So the idea is that there is a conjectured symmetry on the renormalization group flow of gravitational couplings that allow us to define the theory as renormalizable in a non-perturbative sense. This symmetry translates in a renormalization group language as fixed points of beta functions. Okay? I will have to be very brief here. So, I mean, we can discuss at the end more about that, but that's the punchline. So asymptotic safety is essentially an approach that is based on the existence of fixed points on the beta functions for gravitational couplings. The question on whether chiral symmetry breaking can happen or not in asymptotic safety was already investigated a few years ago, first by Astrid Eichhorn and Holger Gies, and later by Jan Melbourne and Jan Pavlovsk. And they found that if you couple gravity to fermions in an asymptotically safe framework, then there's also no indication for chiral symmetry breaking triggered by quantum gravity fluctuations. So it's essentially the same punchline from quadratic gravity. What we also investigated in the last years was how adding more structures to the system can, whether adding more structures to the system can change this structure or can change this result. And we first did this by adding abelian gauge fields to the system. And the main difference here is that once you have an abelian gauge coupling around, you also have non-perturbative effects coming from the abelian gauge field in the ultraviolet regime, or the abelian gauge coupling in the ultraviolet regime. And what we found with the investigation in asymptotic safety plus abelian gauge couplings plus fermions was that if you have a sufficiently low number of fermions, then you can trigger chiral breaking in this system involving gravity plus fermion plus gauge fields. This, for example, provides a way that asymptotic safety can explain the existence of more than one generation of fermions in nature. Okay, but the important point here is that the lower bound that we found is compatible with the number of, charged fermions that exists in nature. So asymptotic safety quantum gravity is still, it passed these tests. More recently, we also added new structures. And in this case, the new structures were non-Abelian structures. So we also add color number to the fermions and a corresponding non-Abelian gauge field. And I will just be very brief here and focus on the main results that I think that we got, which is what I think that is the main result that we got, which is that the interplay between gravity and gauge fields in this case enhances chiral symmetry breaking in the non-Abelian gauge coupling. And this, for example, can be used to put an upper bound on trans-Planckian values of the non-Abelian gauge coupling, which otherwise is a free, if you just think about fermions coupled to non-Abelian gauge fields, in principle, there is no way to impose an upper bound on Planck scale directly in terms of Planck scale physics. But here we do find an indication that there is an upper bound related to this interplay between gravity gauge fields and four fermion interactions. So just to summarize, the idea is that in contrast with neutral fermions, once we couple quantum gravity with charged fermions, and charged under abelian gauge couplings, then we find that this combination could actually trigger chiral symmetry breaking. That's an important difference in comparison with the case where we just have fermions plus gravity. The second lesson from this investigation is that, based on this result, the lesson that we got from this investigation is that asymptotic safety, at least in principle, could explain why we have more than, or why we observe more than one generation of charged fermions in our universe. And essentially, the idea is that if asymptotic safety is indeed realized, this would be inconsistent with a very low number of fermions in our universe, at least from this investigation here. And the lessons from the non-Abelian structures were, well, the first one I didn't mention here in this very brief summary, but the different types of, the idea is that the interplay between fermions and non-Abelian gauge couplings and and gravity, they can generate some kind of symmetry enhancement of the RG flow. And this symmetry enhancement depends on the value of the gravitational coupling around the Planck scale. But the importance, I think the most important result that we found is that gravity actually enhances chiral symmetry breaking related to related to the interplay between gauge fields and fermions. Okay, and this in principle impose an upper bound on the values of the non-Abelian gauge coupling around the Planck scale. So let me now go to my final remarks of this talk, and since I'm probably around going over the time, let me just briefly mention them. So the first important point here is that the existence of light fermions is a non-trivial requirement for quantum gravity theories. And the idea is that, at least in principle, given that gravity is an attractive force, it could lead to a mechanism of chiral symmetry breaking. And if this happens around the Planck scale, this would indicate an incompatibility with what we observe in our universe. And what I try the message that I try to give with this message, with this talk, was that exploring two different approaches of quantum gravity, they both survive to this kind of tests. The first approach was based on an analogy between chiral symmetry breaking, between quadratic gravity and QCD. And in this case here, we found no indication for chiral symmetry breaking, which is a good point for this approach. I mean, this approach is just beginning. It is still unclear whether this kind of analogy is indeed realized. And this is something that I'm very excited about. And yeah, I mean, stay tuned for future work in this direction. The other investigation was related to light fermions in the context of asymptotically safe quantum gravity. And here, the idea is that the interplay, I mean, the main idea of what we explored in the recent years was that the interplay between gravity with extra structures, so for example, abelian or non-abelian gauge couplings, this can in some way enhance the chiral symmetry breaking structure, the chiral symmetry breaking mechanism. But so far, all the results that we have shows that besides this kind of, despite this kind of enhancement, the values that we get from upper bounds, they are still compatible with the observations that we have in our universe. There are some new directions being explored, one of them with Gabriel, our host here, where we are trying to investigate the effect of non-minimal operators on the mechanism of chiral symmetry breaking. And we hope to report on this soon. The other direction that is under investigation is also with Arthur, who is also here today. And the idea is try to, going back to the interplay between torsion, the possible interplay between torsion and chiral symmetry breaking. The idea is now investigate whether fluctuating torsion can lead to chiral symmetry breaking. We already know that a background torsion does not lead to chiral symmetry breaking, but it's still unclear whether a fluctuating torsion can generate chiral symmetry breaking. So we also hope to report on this soon. With this, I would like to thank you for the attention, and yeah, that's it.